Okay, so for those watching the videotape, the correct answer is negative 44.0 kilojoules. We use the first equation as is, and then we reverse the second one, add them together. And again, that was fairly straightforward, but two pretty easy examples show you the process. The longer examples take time to play with them because you have to dig through a bunch of equations and figure out which ones to use and how to use them. So now we've reached the point in the semester where those of you who have an abhorrence for fractions are going to have to move forward and start using fractions to balance chemical equations. Because when we're talking about standard enthalpies of formation, we're talking about a very specific class of chemistry equations. And it is defined as the heat absorbed or evolved, because it can be either positive or negative sign, when 1 mole of substance is formed from the elements in their natural states. And if you're only making 1 mole of the product, then it's not okay to multiply the whole equation by 2 to get rid of those fractions. So when we talk about thermochemical changes of formations, we talk about the standard enthalpy of formation, delta H0 sub F. We add the subscript F to mean formation. The superscript 0 means 25 degrees in 1 atmosphere. These are in your textbook on page 285. They're also in the back of your book in Appendix C2. And I did not include them in the packet because they're too cumbersome to copy in. So when we're talking about these standard enthalpy values, those are the numbers that are associated with the thermochemical equation for the formation of a compound. And they include the subscript F, and they have to meet these following criteria. All reactants are elements in their natural states. 1 mole and 1 mole only of product is formed. We have a balanced chemical equation. All the formulas include subscripts for physical states, and the equation includes delta H0 sub F. So if we look at this, here's an example of a thermochemical equation for the formation, not the information, just the formation of silver bromide. So silver solid plus 1/2 bromine liquid makes 1 mole only of silver bromide solid. Delta H0 sub F is negative 100.4 kilojoules per mole. So that's what one looks like. Now, in your future, when someone asks you to write a thermochemical equation for the formation of whatever, here's how you do it. We look at what we're trying to form, calcium carbonate solid, and we grab the chart and look up the standard enthalpy of formation. Then, I always do these backwards. I start with the product. So I want to make 1 mole of calcium carbonate. I write the proper formula for calcium carbonate, include the subscript for physical state. In its natural state, calcium carbonate is a solid. Then I include the standard enthalpy of formation. I didn't quite leave enough room here. Negative 1206.9 kilojoules per mole. Now I have to figure out, how do I make this? So I have to make it from elements in its natural state. So I look to my periodic chart. Calcium is a metal. It's black on the periodic chart. So it is a solid in its natural state because it's black on the chart. I need 1 carbon. Carbon is an element in its natural state that just comes as a solid. And I need 3 oxygens. Now, we think about the oxygen. Oxygen is a diatomic gas in its natural state. So in order to get 3 oxygens, or 3 moles of oxygen atoms in 1 mole of calcium carbonate, I need 3/2 moles of oxygen. And this is where you get forced into those fractions when you have diatomic elements in their natural states. It is not okay to multiply this by 2. Because if I multiply this by 2, it no longer meets the criteria for a formation reaction because I would then be making 2 moles of calcium carbonate. So when we are writing thermochemical equations for the formation of whatever, then we have to use those fractions if we have a diatomic element. Let's look at the next one, ammonium chloride solid. So we start with our product, ammonium chloride. We write the proper formula. We add in the enthalpy of formation that I went and looked up in the chart, negative 14.4 kilojoules per mole. And to make this, what do I need, class? I need some nitrogen, and it comes in pairs as a diatomic gas. How much do I need? 1/2. What else do I need? Some hydrogen comes in a diatomic gas, and I need 4 of them. So I need 2 there, and what else? Chlorine, also diatomic gas. How much chlorine do I need? 1/2. So now I have a balanced thermochemical equation for the formation of ammonium chloride. So now, just go ahead, take a moment at your seats, and you do those.